talking about books that should be turned into movies. Now, personally, I just think that I should get this out of the way. All of the John Green books, I just really, really enjoy his books, and they would make such cute romantic comedies and just those books. And then, in addition to that, I realized the Series of Unfortunate Events already had a okay-ish movie that changed a lot of things, that covered the first 3 books, but I would really honestly like a movie adaptation, or even like a TV series that lasted for 1 season just to cover the books, because, I don't know, I really liked those books. They were a good time when I was younger, and I appreciated them. So there's that. Apart from that, I'm just going to abuse today's vlog to study for my genetics quiz today. None of what I'm about to say makes sense. I don't even know if I'm really going to post it or not, or if it's even going to be interesting to anyone, but I'm gonna just do a quick review of how to clone a gene. If anybody feels like being an evil mastermind and like finds a really evil gene and wants to clone it, hey, yeah? So step 1, we want to isolate the DNA that we want to clone. Now this is where shit gets boring. There are 3 types of DNA we can clone. Genomic DNA, which is just normal DNA that you would expect to see in any cell in any culture. Then you have cDNA, which is where shit gets complicated. If anybody remembers, we take DNA and we transcribe it into mRNA, and mRNA gets changed a lot. We pull out introns, we pull out other things so that it's ready to be turned into a protein, which makes mRNA much better when you want to translate something or turn it into a protein. So what we do is we take mRNA and we make a DNA copy of it. The benefit of this is all those introns were removed, all the adaptations that we would want to be made to it have been made, so it's much easier to use in a bacterial cell. Which is what we usually use to put DNA into. Anyhow, third option, we can make our own DNA using a PCR thing where we amplify a gene and shit. I did it a couple weeks ago. It's actually really fun. But yeah, that's our third option. However, for this quiz, we're doing genomic DNA because it's the most difficult to describe. Man. So if we're using genomic DNA, there's a shit ton of it. We need to cut the chromosomes up so they're smaller so that we can isolate the one gene that we want. To do this, we're going to use these enzymes that are found in most bacteria. And actually the bacteria tend to use these enzymes to protect themselves from like invading DNA, which sounds really weird, but they get viruses just like we do. And viruses shove their DNA in the bacteria, and the bacteria's like, oh shit, this ain't my DNA! So they have restriction enzymes which cut out DNA which isn't theirs. We use these enzymes to cut up our genomic DNA into smaller pieces so that they're more manageable. So we take these restriction enzymes and they cut up our DNA into little pieces that are like not that big. Anyhow, there are a shit ton of these little pieces now instead of this huge genome. So it's very handy. Some restriction enzymes leave blunt ends on the DNA. The ones that we like leave sticky ends, we call them, where it's like, insert picture here, where it's like a puzzle piece. It fits together with other DNA better than just putting 2 straight pieces together, you know? So, now that confusing bit's out of the way, it's time for something more confusing. We're going to choose an appropriate cloning vector. For us, it would be bacterial plasmid DNA. Very, very tiny, round. Bacteria don't really need it. They have their own genomic DNA that determines most of their life cycle. Plasmid DNA they kind of use. They have a really weird form of sex where they poke each other with their plasmids. So plasmids aren't too terribly important to them. So what we do is we take their plasmids, and we cut them up with the same enzyme we used before, so that it'll have the same ends that our DNA has, so that our DNA can stick with those plasmids. So then we put our DNA that's been cut up and the plasmid DNA that's been cut up in a test tube. They, of course, end up sticking together. And you end up getting like 1 slice per 1 plasmid because the plasmids can only handle so much DNA because they're teeny tiny and they can't take all that shit. That's too much. It's too much. So that's done. And then, of course, we need to glue the stuff together. So we use ligase, which is like DNA glue, makes phosphodiester bonds. And then, now that we've got all of these like hundreds of pieces of useless DNA stuck into plasmids and like 1 piece somewhere that is the gene we actually wanted stuck to a plasmid DNA, we put all these plasmids back into bacteria. The only issue is the bacteria we like to use doesn't like getting plasmids put into it. Some of them are cool with that shit, but E. coli's like, bitch, no. So we kind of have to torture it a little bit. We add heat and calcium chloride, and then it just like shocks the hell out of it, and it accepts a plasmid, regardless of whether or not it wants to. So there's that, and then, yeah, we have actually marked the strand of DNA that we wanted to be marked with a antibiotic resistance gene, so we kill off all the ones we don't want, and we have our beautiful gene that we cloned. It's a bit excessive to clone a gene, but you know, it's handy. It's how we make insulin. I feel like I should just put a skip here button, but that really helped me study for my test. If that's any excuse for that. But yeah, so that's what I did this week. I studied for genetics in vlog form. And yeah, Shelby, I'll see you tomorrow. Can't wait to get your letter. Bye, guys.